What if our very definition of life is nothing more than the bias of a single planet? What if our belief that carbon is the only foundation of life has fundamentally narrowed our questions about the cosmos? Every form of life on Earth depends on a single element, carbon. DNA, proteins, lipids, all of it built upon a carbon skeleton. Carbon has 4 bonding hands, capable of constructing molecules of breathtaking complexity. The number of carbon atoms in our bodies reaches astronomical scales on the order of hundreds of quintillions. We're talking about the same order of magnitude as the number of stars in the universe. But here's what I keep wondering. When we look across the entire cosmos, why must life be carbon-based at all? Silicon, sulfur, nitrogen, these two are elements capable of generating complex chemistry. Could the very thing we call life be an extraordinarily biased conclusion drawn from a single sample called Earth? Today, we confront carbon chauvinism head-on, the assumption that carbon is the one and only foundation of life. And we'll explore just how strange the chemistry of life elsewhere in the universe might be. By the time this video ends, the very meaning of the word life may be shaken to its core. Chapter 1: The Miracle of Carbon and Its Limits. Let's begin with why life on Earth chose carbon, or rather, why carbon was chosen by life. What makes carbon so special? It comes down to those 4 bonding hands. It can bond with other elements in multiple directions, forming chains, rings, and intricate 3-dimensional structures. Chemical databases list hundreds of millions of organic compounds, and that number keeps growing at this very moment. Almost no other element can generate this diversity of molecules. What's more, carbon compounds share an exquisite compatibility with water as a solvent. Water, as a polar solvent, dissolves many ions and biomolecules, while refusing to mix with hydrophobic molecules like oils. And it's precisely this refusal to dissolve that gives rise to self-organizing structures like cell membranes. Water isn't simply convenient for life. The very properties of water shape the architecture of life itself. But I want to pause here and consider something. Has Earth's environment been optimized for carbon and water, or did carbon and water adapt to Earth's environment? This question runs deeper than it first appears. Carbon has its constraints. In oxygen-rich, oxidizing environments at high temperatures, many organic molecules break down and stabilize as carbon dioxide. However, in reducing environments with little oxygen, carbon can persist even at high temperatures as methane or carbon monoxide. Carbon's fate is determined not just by temperature, but by the chemical air quality of the planet it inhabits. And here's where a crucial question emerges. If most planetary environments in the cosmos differ chemically from Earth, would carbon function the same way there? Or could an entirely different chemistry be nurturing an entirely different kind of life? Carbon is Earth's answer, but there is no guarantee it is the universe's answer. So what elements could serve as carbon's replacement? And what would life look like if they did? Let's turn our attention to carbon's rivals. Chapter 2: Silicon, Sulfur, and the World of Different Chemistries. The first rival scientists turn to is silicon. It sits directly below carbon on the periodic table and likewise has 4 bonding hands. Of all elements, it most closely resembles carbon in chemical behavior. So why didn't life on Earth choose silicon? Here's where it gets fascinating. When carbon oxidizes, it becomes carbon dioxide, a gas that life can absorb from the atmosphere and recycle. But when silicon oxidizes, it becomes silicon dioxide, rock, sand, a solid. That means breathing and excretion become extraordinarily difficult, unless you're on a planet hot enough to melt rock. Silicon also lacks the diversity of multiple bonding arrangements that carbon possesses, limiting its capacity to generate complex molecules. The prevailing view among researchers is that silicon cannot simply be swapped in for carbon. But shift the perspective, and the story changes entirely. Cassini spacecraft radar observations confirmed that Saturn's moon Titan is blanketed with liquid lakes of methane and ethane. Surface temperatures average around -179 degrees Celsius. Water freezes completely solid there. Yet, the hydrocarbon lakes remain liquid. If life exists on Titan, It almost certainly uses methane, not water, as its solvent. It might still be carbon-based, but its metabolism would be fundamentally unlike anything on Earth. In 2015, a research team at Cornell University theoretically proposed a cell membrane structure that could remain stable in Titan's methane environment. They suggested that acrylonitrile, a nitrogen-containing organic molecule, could form a membrane structure called an azotosome, capable of functioning in extreme cold. However, subsequent research raised objections, arguing that forming such membranes might be thermodynamically prohibitive, and the debate continues. This is science in the act of moving from hypothesis toward verification. And now, a mission is underway to investigate Titan's mysteries firsthand. NASA is advancing Dragonfly, a rotorcraft-style mission designed to examine Titan's organic chemistry and habitability on the surface itself. Titan has become one of the most critical targets for testing the possibility of life in a world without water. Let's also turn our attention to sulfur. Near deep-sea hydrothermal vents on Earth, microorganisms, including both bacteria and archaea, thrive by harnessing the oxidation-reduction reactions of sulfur as their energy source. This is a metabolism that neither photosynthesizes nor breathes oxygen. It eats sulfur. If a planetary environment existed with high temperatures and high sulfur concentrations, a form of life centered on sulfur-based metabolism could conceivably take hold. Let's think about what this means. What life may require is not carbon, but a mechanism capable of sustaining complex chemical reactions continuously. Carbon may be just one answer to that requirement, and the cosmos may hold countless chemical answers we have yet to imagine. Our conception of life on Earth is a single planet's single solution. The universe may have prepared far more solutions than our textbooks contain. And here's where a crucial question emerges. If this possibility of different chemistries changes the very way we search for life, what then? Let's venture into the most fundamental questions in astrobiology. Chapter 3: Beyond Carbon Chauvinism, Redefining Life. In astrobiology, there's a concept known as the Goldilocks zone. The idea is that planets at just the right distance from their star, within a temperature range where water can exist as a liquid, are the candidates for harboring life. Liquid water remains the most important indicator of life. Yet at the same time, theoretical and observational research into habitability in non-aqueous solvents and environments, hydrocarbon lakes, acidic clouds, is beginning to expand. Consider this for a moment. What if life can thrive in cold liquid hydrocarbon environments like Titan's? What if life using different solvents exists even in the ammonia clouds of Jupiter's atmosphere? Our search space would expand by orders of magnitude. And here's where we face a far more fundamental question. How do we define life? Various definitions exist, but self-replication, metabolism, and boundary formation, compartmentalization, are generally cited as key elements. But where did this definition come from? It emerged from observing life on Earth and extracting its common features. In other words, our definition of life is an induction drawn from a sample size of one. We are attempting to derive a definition applicable to the entire cosmos from a single case, Earth. Scientifically speaking, this is an extraordinarily high-risk generalization. Some physicists and astrobiologists are working to disentangle life's universal definition from carbon and water. One perspective holds that the essence of life is a local decrease in entropy, a process that maintains order in defiance of surrounding disorder. Another holds that information processing, a system that absorbs, processes, and uses environmental information to determine its next state, may be the core of life. And in 2023, a radically new approach called assembly theory was published in Nature. It proposes a way to mathematically detect the signatures of life, regardless of what it's made of, by calculating how many complex steps were required to assemble a given piece of matter. This theory, which seeks to use complexity itself as the indicator of life regardless of whether it is carbon-based, has drawn intense interest from space exploration agencies including NASA. If that's the case, life may not need to be carbon-based at all. Carbon chauvinism is not merely a fondness for a particular element. It is the exposure of an epistemological limit, a revelation of just how Earth-centric our answer to the question, "What is life?" truly is. When we explore the cosmos, we are searching for our own mirror image. But if life is written in a chemical language utterly unlike anything we can imagine, we might pass right by its existence without ever recognizing it as life. What astrobiology is most urgently grappling with now is not how to search for life, but the redefinition of life as a concept itself. This is a scientific question, and simultaneously a deeply philosophical one. Let's take stock of what this exploration has revealed. Chapter 4: The Endless Quest. Today, we've explored a central question: does life require carbon? We examined why life on Earth chose carbon, its overwhelming chemical advantages. And at the same time, we began to see that those advantages hold only under the specific environmental conditions found on a planet called Earth. Silicon, sulfur, nitrogen. Scientists are now seriously exploring the possibility that different elements could carry the chemistry of life in different planetary environments. Let me share 3 insights from today's exploration. First, carbon is only Earth's answer. Carbon's 4 bonds and the diversity of organic compounds represent a solution optimized for Earth's temperature and its solvent water. The universe holds countless planets with different temperatures and different chemical environments, where other elements could serve as life's scaffold. There is no guarantee that carbon is the universal answer. Second, the solvent need not be water. Titan's methane lakes, the ammonia clouds of Jupiter's atmosphere, even in environments where liquid water doesn't exist, other solvents could serve as the stage for life's chemistry. If the premise that no water means no life collapses, the definition of habitable places in the universe changes at its foundation. NASA's Dragonfly mission is seeking answers to that question on the ground itself. Third, redefine the definition of life. What we call life was defined inductively from a single sample, Earth. Entropy reduction, information processing, assembly theory. By redefining life from a more universal perspective, we may develop the eyes to perceive life in the cosmos that we could not see before. These 3 insights all point toward a single conclusion. The search for life in the cosmos must transform from a journey searching for Earth life's mirror image into an intellectual revolution that questions the very concept of life from the ground up. This exploration has left me profoundly astonished. At first, the phrase carbon chauvinism struck me as slightly absurd. But the more I think about it, the more I realize it is a sharp critique that reveals the structural limits of human cognition itself. We may only be capable of recognizing life in the forms we already know. That is a problem of science, and simultaneously a problem of human imagination. It is a question that is, in equal measure, terrifying and beautiful. Let me ask you this. If silicon-based life, or something we cannot even recognize as life, exists somewhere in the cosmos, how would we ever determine that it is alive? Could a mathematical framework like assembly theory provide the answer? And if life on Earth turns out to be an exceptionally narrow form of life in the universe, how would that change the dignity and meaning we attach to existence itself? There are no answers to these questions yet. But, continuing to ask, that itself is the force that drives exploration forward. Astrobiology is only now beginning to confront these questions directly. And we are fellow travelers on that intellectual journey. When you return to everyday life after this video ends, try something. Choose one assumption you take for granted and ask yourself, what if this is a bias unique to Earth? About life, about consciousness, about what normal even means. Carbon chauvinism lurks not only in discussions of life, it hides in every corner of how we think. To question your own obvious, that is where a mind shift begins. The vastness of the universe gives us the courage to do exactly that. Share your insights in the comments below. Your questions are the force that propels this channel forward. Thank you for staying with this intellectual journey all the way to the end. What is life? What is consciousness? Where is the universe headed? Mindshift is a channel that continues its exploration anchored to these 3 core questions. At the intersection of science's cutting edge and philosophy's deepest currents, we open a new door of inquiry with every episode. If you wish to continue this journey, subscribe and turn on notifications so you don't miss the next exploration. Until next time.